In this video, we're going to explore a little bit more deeply into the idea of compounds and molecules, and then start to discuss how we come up with chemical formulas and the names for chemical compounds. As we talked about earlier, a compound is a combination of two or more elements in a definite ratio. Compounds will fall into two major categories. We'll have either ionic compounds, which are typically composed of maybe a metal and a nonmetal, or maybe a metal and a polyatomic ion. The key term here, however, is going to be that ionic compounds are composed of ions of some sort, which we'll talk about in a little bit. We can also have molecular compounds, which are going to be formed by two or more nonmetals coming together. One molecule is considered to be the smallest unit of a compound that still retains the characteristics of that compound. It's important to note that the character or the properties of individual elements are lost when forming a compound. For instance, the element sodium is a very soft silvery gray metal. You can cut it with a butter knife. It is very reactive with water. If you throw it in with water, it can catch on fire or possibly even explode. And then we also have the element chlorine, very toxic gas. If you mix chlorine with water, it can form hydrochloric acid. So if you get it in your eyes, you can form acid in your eyes. Breathe it in, you can form acid by reacting with the water in your lungs. Incredibly toxic sort of chemical. If, however, we put the two of them together in a compound, we form NaCl, otherwise known as sodium chloride, and then we can put it on our popcorn for a delicious snack. It is no longer going to blow up if we put it in water, and luckily it's not going to form hydrochloric acid when we eat it. So the characteristics of the individual elements are now completely lost. We have formed a new compound. Ionic compounds are one of the major class of compounds that we'll study. They're going to be made up of ions, which are atoms or groups of atoms that have a negative or a positive charge. Many of the familiar compounds that we know of are ionic compounds. For instance, as I discussed in the previous slide, table salt, sodium chloride, is an example of an ionic compound. Ionic compounds in general are referred to as salts. So when you hear that term, don't think of only the familiar salt of sodium chloride. Technically speaking, from a chemical perspective, all ionic compounds are salts. So what is an ion? An ion is an atom or a group of atoms that has a positive or a negative charge. Previously, we talked about atoms as having an equal number of protons and electrons, making the charge neutral overall. However, many atoms, in order to become stable, will either gain or lose electrons. If an electron is lost, remember electrons have a negative charge, that will result in an ion with a positive charge that we call a cation. If an atom gains an electron, that will make the atom negative overall and become a negative ion, which we refer to as an anion. For example, if we have a magnesium atom, magnesium is a metal which is going to tend to lose electrons in order to become stable. Magnesium has an atomic number of 10, meaning there are 10 protons in the nucleus. And so a neutral magnesium atom will also have 10 electrons, giving us an overall charge of 0. In order to become stable, however, magnesium will lose 2 electrons. It's still magnesium, therefore it is still going to have the 10 protons, but now we only have 8 electrons. Therefore, there are 2 additional positive charges as compared to the negative charges, leaving us with a charge of 2+ on the magnesium ion. Fluorine, on the other hand, has an atomic number of 9, and so 9 protons. A neutral fluorine atom therefore has 9 electrons for a neutral overall charge. In order to become stable, fluorine will gain an electron. It still has its 9 protons, it's still fluorine, but now it has 10 electrons. Therefore, it has one additional negative charge compared to its positives, for a charge of 1 minus on our fluorine anion. Generally speaking, metals will tend to lose electrons, forming positively charged cations. Nonmetals will tend to gain electrons in order to form negatively charged anions. We can see several examples of charges on this chart. And as we said, our metals, you can see all tend to form positive charges, whereas nonmetals will tend to form negative charges. We can also see a pattern starting to form. Our group 1 metals tend to form charges of 1 plus. Our group 2 metals tend to form charges of 2 plus. Transition metals, however, are not quite as easily as predicted. Our group 5 nonmetals tend to form -3 ions. Our group 6 nonmetals tend to form -2 ions. And our group 7 metals, as well as hydrogen, can form -1 ions. We need to keep in mind that hydrogen is an exception to many rules in chemistry. In this case, hydrogen has both the ability to form a positively charged cation or a negatively charged anion. We'll see in a little bit how we'll be able to tell the difference depending on the compound that it's in. Ultimately, atoms will gain or lose electrons in order to obtain the same number of electrons as the nearest noble gas. If we look at lithium, for example, lithium, with its atomic number of 3, has 3 protons and 3 electrons in the nucleus. The closest noble gas to lithium is helium. And so the easiest thing for lithium to do is to lose 1 electron, so it has 2 electrons in its nucleus, the same number of electrons as helium. And so lithium will tend to lose 1 electron and form a +1 charge. Magnesium has 12 electrons in its nucleus. The easiest thing for magnesium to do is to lose 2 electrons to then have a total of 10 electrons, which is the same number that neon has. So if magnesium loses 2 electrons, it forms a charge of +2. One thing this leads us to is being able to predict the charge of ions based on the group number of the atom. All metals in group 1, our alkali metals, will behave in the same way that we talked about with lithium. They'll tend to lose 1 electron and form +1 charged ions. All of the alkaline earth metals in group 2 will tend to lose 2 electrons and form charges of +2. The transition metals are a little bit different and not as easily predicted. As a result of that, our transition metals are going to have variable charges. And we'll talk about how we deal with that later on. Looking at our halogens, though, if we take a look, for instance, at bromine, atomic number 35, 35 protons, 35 electrons. The easiest way for bromine to get the same number of electrons as a noble gas is to gain 1 more, so it'll have 36 electrons, the same as krypton. And so bromine has gained 1 electron, leaving it with a charge of -1. Likewise, all of our halogens will do the same, and all tend to form -1 charges. Similarly, all of our group 6 nonmetals will tend to gain 2 electrons and form charges of -2. All of our group 5 nonmetals will tend to gain 3 electrons and form charges of -3. So we can use the periodic table in order to tell what the charge will be on most of our ions. Ions will have a slightly different name than the atoms from which they came. For positively charged cations, all we do is add the word ion at the end. And so Na plus will simply have the term sodium ion. We know that it is going to be a positively 1 charged ion because of what we discussed on the previous slide. Sodium is in group 1, and all of the group 1 metals will have a +1 charge. Anions, we actually change the name of slightly. We take the end off the name and replace it with IDE. So chlorine 1- will be referred to as the chloride ion. We know that the chloride ion will have a 1- charge because it is a halogen in group 7, and all of the group 7 atoms will form -1 charged ions. Since they can have variable charges, we have to treat the names of transition metals a little bit differently when they form ions. For instance, copper can form either a +1 charge or a +2 charge. The way that we tell the difference between the two is by using a Roman numeral in the name. Copper that has a 1+ charge is referred to as the copper 1 ion. Copper with a 2+ charge is referred to as the copper 2 ion. So if we say copper 1, we know that we're talking about copper with our 1+ charge. There are a couple of notable exceptions to this. There are a couple of elements who actually do not have a variable charge even though they are transition elements. The most notable ones are silver, which will always form a 1+ charge, and zinc, which will always form a 2+ charge. And so we usually refer to those simply as a silver ion or a zinc ion, since we know that silver will be a +1 and zinc will be a +2. And recall that for our nonmetals, we always change the end of the name to IDE. And so, for instance, nitrogen becomes nitride, phosphorus becomes phosphide, oxygen becomes oxide, and so on. Hydrogen would become hydride. What we've been discussing so far are what we call monatomic ions. Ions that are formed from just one element. Polyatomic ions are another type of ions that form from a group of elements. And so we'll have 2 or more elements bound together that overall have an associated charge. This table lists the more common polyatomic ions. And so, for instance, if we have a molecule NH4 with a +1 charge, that's referred to as the ammonium ion. CO3 with a -2 charge is referred to as the carbonate ion. NO3 with a -1 charge is the nitrate ion. NO2 with a -1 charge is the nitrite ion, and so forth. This chart represents some of the more common polyatomic ions. You will have to memorize the formulas, charges, and names of the polyatomic ions on this chart. This leads us to how we come up with the formulas for ionic compounds. Ultimately, when an ionic compound forms, it will be neutral. And so the amount of positive charge from the ions will be equal to the amount of negative charge from the ions. And so let's remember that the ions of our main group elements is predictable. The metals in 1A to 3A will tend to lose electrons and form cations. Our nonmetals in groups 5 to 7 will tend to gain electrons to become anions in a predictable way. For instance, magnesium in group 2 will tend to form a magnesium 2+ ion. whereas bromine, which is in group 7, will tend to gain 1 electron to form a bromide 1- ion. One of the more common combinations that we will see is a cation formed from a metal combining with an anion formed from a nonmetal. When the two of these come together in an ionic compound, the overall charge will be 0, so the total amount of pluses will equal the total amount of negatives, and we can predict our ion charge by using the periodic table. We'll look at some examples of this in just a minute. When looking at ionic formulas, we have to remember that transition metals can have more than one type of charge. And so, if we're given a formula of FeCl2, we have to use what we know about Cl in order to figure out what the charge is on our iron ion in this case. We know that Cl has a charge of -1. In this formula, we have 2 Cl ions. Therefore, we have a total of 2 negative. We have 1 iron, which must offset that 2 negative. Therefore, the charge on iron in this case must be +2. If we have a formula of FeCl3, our chloride ion has a charge of -1. In this case, we have 3 chloride ions for a total of a -3 charge. We still just have 1 iron ion, and that 1 iron ion must offset the 3 negative from chlorine. Therefore, in this case, the iron must have a charge of +3. When writing chemical formulas from ions, we can use what we call the crossover rule to make sure that our overall charge is 0. This will apply to monatomic ions as well to polyatomic ions. We do have to remember, however, that with polyatomic ions, we might have to use parentheses to indicate the total number of the entire polyatomic ion. We'll see some examples of that in a minute. And so, for example, if we are coming up with the formula for sodium sulfide, we know that sodium, symbol Na, is in group 1, so it will have a charge of +1. Sulfide is the ion of sulfur, which is in group 6, so we'll have a charge of -2. So here's our Na +1, our sulfur with a -2, and we can see the crossover rule. We have a 1+ on sodium. That will become our subscript for sulfur in our chemical formula. Likewise, our charge of 2- on sulfur will become our subscript on sodium in our chemical formula. In chemical formulas, if we have 1 as a subscript, it is understood the 1 is there, and so it is omitted, leaving us with a formula for sodium sulfide of Na2S. Let's take a look at several examples. If we have, for instance, a magnesium ion with its charge of 2+, and a chloride ion with its charge of 1-, if we use our crossover rule, then we see that our subscript for magnesium will be 1, so we won't write that. Our subscript for chlorine will be 2, so we get MgCl2. If we have sodium, 1+, coming together with nitrogen with its 3-, we use our crossover rule, and we get a formula of Na3N. Let's look at a polyatomic ion. Calcium forming a 2+ ion, and NO3 forming its 1+. Our crossover rule tells us that the subscript on calcium is going to be 1, and our subscript for nitrate is going to be 2. This is where we must use parentheses. We must put nitrate in parentheses and put our 2 outside that to indicate that we have 2 total of the nitrate ions. If you only have 1 of the polyatomic ion in an example, you do not need to use parentheses. For instance, if we have our sodium with its 1 plus charge, and now we have also nitrate with its 1 minus, our crossover rule tells us that the subscript is just 1 for each. We don't need parentheses since it's just 1 nitrate, and we get a formula of NaNO3. The crossover rule is a very helpful tool in finding the formula for ionic compounds. We have to remember, though, that ultimately it works because it gives us the ratios we need in order to balance out our positive and our negative charges. We always want the lowest whole number ratios. So let's look at another example. If we have calcium with a 2 plus ion and oxygen with a 2 minus ion, our crossover rule would give us Ca2O2. With ionic compounds, though, we are always looking for our lowest whole number ratio. Therefore, the actual formula would simply be CaO. So be careful when you're using the crossover rule that you don't fall for that trap. You always want to reduce down to the lowest whole number ratio. You want the lowest ratio required for the pluses to balance out the negatives. In this case, it only takes 1 of our Ca2 plus ions to balance out 1 oxygen 2 minus ion. Let's look at one more example. Let's look at what the formula would be for magnesium phosphate. Magnesium has a 2 plus charge. Our phosphate polyatomic ion has a 3 minus charge. And so our crossover rule tells us that our subscript for magnesium is going to be a 3. Our subscript for phosphate is 2. We need to put that in parentheses. And so we come up with a formula of Mg3PO4 Here's a bunch of ionic formulas for you to try. Each of the ions is given. Come up with the chemical formula. In the case of the transition metals, remember that the Roman numeral tells you what the charge is for that particular metal. Pause the video now, try to come up with the ionic formulas, restart the video to check your answers. Here are all of the answers. If you missed some, go back and check. Try to find out what you did wrong. Now that we've seen how to write chemical formulas, we need to discuss how to come up with the names of ionic compounds. The cation is always named first, and the anion is always named second. A monatomic cation simply takes its name from the name of the element. In other words, if we are naming NaCl, our cation is Na, and so the name of it is simply going to be sodium. A monatomic anion is named by taking the root of the element and adding IDE. And so in this case, chlorine, we are going to change to chloride. And so the name for NaCl is going to be sodium chloride. Remember that the charges of the main group elements do not change. Therefore, if I give someone the name sodium chloride, they will be able to come up with the formula because they know that sodium is going to be a 1 plus, chloride is going to be a 1 minus, leading us again back to the formula NaCl. Remember, though, that transition metals will form variable charges. Therefore, our name has to indicate what the charge on that metal is. For instance, chromium can form either a +3 ion, which we would name chromium 3, or a +6 ion, which we would name chromium 6. And so that charge will be reflected in the final name of the compound. In this example, we have iron 3 coming together with oxide with its -2. And so if we remember our crossover rule, that's our iron 3 plus and our O2 minus, leading us to the formula Fe2O3. But in this case, since the iron came from iron 3, that is now reflected in our name, iron 3 oxide. Remember, part of the idea here is to be able to go back and forth between the names and the formulas. And so if, for instance, you were told that you had iron 2 oxide, that would tell you that you're dealing with iron with a 2 plus charge. And your oxygen still has its -2, giving us a resulting formula of FeO in this case for iron 2 oxide. Let's look at some examples. Remember that if the metal is group 1 through 3, we're just going to name the ion using the name of the metal. We do the same thing, like mentioned before, with silver or zinc, or also cadmium, which will have a +2 charge. And so BaI2 will be named barium iodide. MgCl2 will be named magnesium chloride. AgF is silver fluoride. AlBr3, aluminum bromide, and Ca3N2, calcium nitride. Here are several more examples for you to try. Pause the video, come up with the name from the chemical formula, and then restart the video to check your answers. Remember that in these cases, the name of the cation simply comes from the element, and in the name of the anion, we change the name to IDE. We have to treat molecular compounds a little bit differently. Due to the ways that nonmetals combine, they can do so in multiple ways. For instance, when carbon and oxygen come together, we can either have one carbon atom and one oxygen atom, which would be carbon monoxide, or one carbon atom and two oxygen atoms, which would be carbon dioxide. Therefore, simply saying carbon oxide, as we would have for ionic compounds, does not give us the information that we need in order to come up with the chemical formula. Because of this, in molecular compounds, we need to specify the number of each atom with a prefix. And so we see some examples here. In BlCl3, we have one boron atom and 3 chloride atoms. Therefore, we have boron trichloride. In SO3, one sulfur atom, 3 oxygens for sulfur trioxide. In NO, one nitrogen atom, 1 oxygen atom, so we get nitrogen monoxide. Note that we drop one of the O's here. We do not write monooxide. It is simply monoxide. Also, if there is only one of the first atom in the compound, we drop off the mono. So we do not write mononitrogen monoxide. It is simply nitrogen monoxide. In the case of N2O4, it is dinitrogen for 2 nitrogen atoms, and it would be written as tetroxide. We would drop off the O and simply write it as tetroxide. It is vital to note that we only use these prefixes for molecular compounds, which is when two non-metals will come together. We do not use these prefixes for ionic compounds, which are combinations of a metal and a nonmetal, or polyatomic ions. For instance, CaBr2. This is an ionic compound composed of the calcium cation and the bromide anion. Therefore, our name for this compound is simply going to be calcium bromide, not calcium dibromide. That would be incorrect, and it would be marked as such. On the other hand, if we have the compound N2O5, that is a molecular compound composed of two nonmetals. In this case, we do have to use the prefixes. And our name would be dinitrogen pentoxide. And so to recap that, remember, you do not use prefixes for ionic compounds of a metal and a nonmetal, or polyatomic ions. You do use the prefixes when it is two nonmetals coming together. With that in mind, and so, take some time now and come up with the names of these compounds. You have to remember several things as you're doing this. First, you have to identify if it is an ionic or a molecular compound. If it is ionic, then you do not use the prefixes. If it is molecular, you do. If there is a polyatomic ion, then you have to be able to give the name of that. So you begin to see why it is so important for you to memorize those polyatomic ions. You have to be able to see the combination of CO3, for instance, and recognize that that is the carbonate polyatomic ion. Don't forget that if it is an ionic compound and your cation is a transition metal, you have to be able to figure out what the charge is on that and incorporate that into your name. And so pause the video now, come up with the names of these compounds, and restart the video to check your answers. And here they are. So just to walk through them a little bit and the process is going on here, NaCl is an ionic compound. Sodium is a group 1 metal, so we don't have to worry about that in the name. So we just have sodium chloride. Same thing here. Calcium is a group 2 metal, so we have calcium bromide. Here we have sodium coming together with our phosphate polyatomic ion for the name sodium phosphate. In these two cases, we now have molecular compounds. Carbon and oxygen are both nonmetals, and so our name has to incorporate the number of each into it. So we have carbon monoxide for 1 oxygen, carbon dioxide for 2 oxygens. And we come back to a couple more ionic compounds, but now our metal is iron, which is the transition metal. So we have to use the fact that oxygen has a -2 charge. In this case, we have 1 of each, therefore the charge on iron in this case has to be 2 for iron 2 oxide. Now we have 3 oxygens for a total charge of -6. We have 2 irons, therefore the charge on each iron must be +3 for iron 3 oxide. Here we have 2 polyatomic ions coming together, so we just use the names of those for ammonium nitrate. Another ionic compound, magnesium and oxygen. Magnesium is a group 2 metal, so we just use its name of magnesium oxide. Ionic compound composed of the calcium ion and the carbonate polyatomic ion. Here we have another molecular compound. Nitrogen and oxygen are both nonmetals, so we have to use our prefixes, 2 nitrogens for dinitrogen, 5 oxygens for pentoxide. An ionic compound using aluminum and nitrogen for aluminum nitride. Zinc sulfate. Remember that zinc is a transition metal, but it is one of our only exceptions where we do not have to use the Roman numeral because the charge on zinc is always +2. And then, probably our most challenging ionic compound. Chromium is a transition metal, so we have to incorporate the charge into its name. We have 7 oxygens for a total negative charge of -14. We have 2 chromiums, which must add up to a +14. Therefore, each chromium must carry with it a +7 charge, for our name of chromium 7 oxide. There's a lot going on in this video. The skills that we learned here, though, in putting together ionic formulas and in naming compounds, are skills that we will use all through the semester. Once again, as before, I urge you, if you do not understand this after watching the video and reading the book, be sure to come see me for some additional help or go see a tutor at the Learning Commons. If you fall behind here, you will be hurting yourself for the rest of the semester. These are key skills that we will continue to use. Thank you.